version. Classical version of the classical the exponent smoothing method, which includes single or simple exponent smoothing as well as for linear. So we discussed last week, we discussed two. So recall that single or SES, single or simple exponent smoothing is used when we have horizontal trend vector. So just there is no upward or downward, and then there is no signal variation. So we use single exponent smoothing or SES. So remember the idea of this method is to allow us to update the level, and then we use the update level wherever we have new information from new observed value, we update level. So what is level? I explained to you is quite equivalent to the estimate of the value on the trend estimate when we form classical convolution. So we have S, T, and then the N component. So basically the T. So basically the value of the series, or the value of the estimate of T trend is actually quite equivalent to the value of level of the series. So we update the level when we have a new of information, and then at the same time we also take into account the previous estimate level, so that we do not 100% rely on the new observed values. And then after we update, we use the value to produce forecast for the next observation. And then we also have, so recall that one, in terms of the body constant alpha, we can either simply set any value or we estimate through optimization. Okay. And then we have second method called linear, which is suitable when we have trend. When we have trend, upward or downward, doesn't matter lah, upward, downward. So if upward, our the growth term ET is supposed to be positive, this one. If downward trend, that's supposed to be negative value. But again, the idea is still the same. When we have new information from new observed value of Y, we update level using OFA average by taking a portion of new information as well as a portion of the previous estimate, pre-estimate. This one actually we use the previous level plus this one. I think last week I hope you already understand. Okay, so we use this one just like a pre-estimate of level. Okay, before we take into account the new information, so we just pre-estimate using the previous estimate level, because it has trend, it must have some additional value, increase, increment. Okay, so we have this one plus estimate growth one period, because it is for LT, current time. This one we use the estimate of the previous time, T minus 1, plus growth one period. If a pre-estimate of LT at time T, and then we also take a portion of new information from U1 as well. And after we update growth, we re-estimate of growth for one period by taking the difference between the last two levels, and then at the same time also we also take into account the previous estimate of growth from period as well. And then we use that information to produce forecast for the next observation. So M, how many step ahead? If only one step ahead, normally for example only one step ahead. Okay, so M equal to 1. But for our sample is combination. So from the last observation, the next one is one step ahead. For the last observation, for the next two is 2 step ahead, 3 step ahead, and so on. Because we no longer have new information, new observation of Y, and then we can produce multi-step ahead, 1 step ahead, 2 step ahead. If you have multi-data, maybe we will forecast for the next one, and then forecast for the next 2 months, for the next 3 months, and so on. So in terms of the smoothing constant, we have two for this one, alpha and beta. So again, you actually can assign any value that you think suitable, while alternatively we also can use optimization to find optimal value of alpha and beta that gives us smallest value of SSE, for example. Okay. So that's called linear. Now we go to the next model for the case of series that has seasonal variation. So we have we test trend and seasonality. So we have whole winters additive as well as whole winters multiple model. Alright, so seasonality models are usually classified as additive or multiplicative, just like what we discussed in the earlier lecture on character decomposition. So we have additive seasonal variation when the magnitude of seasonality just constant throughout of the series for the entire data set. But for the case of if the magnitude of seasonal variation increase as the level increase, the value of level increase, then we call it multiplicative seasonal variation. Or if you say the level decrease and then the magnitude of seasonal variation decrease, the one they want multiplicative seasonal variation. So the additive model is appropriate if the magnitude of the seasonal fluctuation does not vary with the level of series. The multiplicative model is appropriate if the seasonal fluctuation increases and decreases proportionally with increases and decreases in the level of series. So the two examples given earlier in lecture 2, the mistaken, so we discussed decomposition. You can see what one the example of the case of series that considered to have additive seasonal variation, and then another one when we have multiplicative seasonal variation. So the model is similar to whole linear model. It again has level and trend terms and corresponding constant alpha and beta. So meaning that we still have equation to update level, and then at the same time also have an equation to update the growth term in T, level LT. Okay, and then in addition, it has seasonal index and a corresponding smoothing parameter gamma. So the new smoothing parameters, gamma controls how quickly the method reacts to present changes in the pattern of seasonality. If gamma is small, the method reacts slowly. If gamma is large, the method reacts more quickly. So as with whole linear model, there are equations for updating the level and trend terms, and there is an extra equation for updating the seasonal indices. So we have additional equation, this one, for seasonal index, seasonal component. So you notice that this one is quite similar to the whole linear, except that this one, except for this one, so instead of using YT, we use seasonally adjusted value. Okay, so this one, because we want to update level, we need to remove the seasonal one. We want to update level using new information. Before you use the information, we have to remove the seasonal variation part of the series. So YT minus ST for us to produce what we call as just like deseasonalized, to remove seasonally adjusted. Remember when we form character decomposition, so we have when we want to calculate seasonal adjusted value. So the y for additive, y minus s. Remember that one when we do decomposition same. Okay. So this one we do not use the YT because this series has seasonal variation. So we have to remove the seasonal component first, seasonal variation from that series, and use seasonally adjusted value. Seasonally adjusted after we remove seasonal and we have seasonal adjusted, and then use the seasonal value to update the level. Okay. And then the same just like before. We also take into account pre-estimate of the current level by using the previous level plus growth for one period. Okay, the last updated or the last estimated value for the level, the previous one, at time t minus 1, plus growth for one period, estimated value for growth one period of the previous one. So the previous level plus growth for one period give us pre-estimate for the current one at t, the current t. Okay. So this using the estimate at time t minus 1, we pre-estimate, okay, level at time t, the next one. Okay. So and then based on the value of alpha. If normally, I mean again, alpha normally we set between 0 and 1. Alpha between 0 and 1, so that what we have here is it can be considered as weighted average. Okay. So if this one 0.5 and then the remaining 0.5 here, so 50% from new information, and then 50% using the previous estimate of level and growth for one period. Okay. So just like before, when we have new updated our level, and then we can update our growth, re-estimate. So we re-estimate our estimate of growth one period. So by taking the difference between the last two levels, time LT and LT minus 1. So it gives the increment, how many the latest increment for the last two levels. And then again, this one also we take into account the previous estimate. So this one, the previous estimate, this one, the new information. And then we have a new equation. This one actually equation for seasonal index. So seasonal index, if you recall that for classical decomposition, how we calculate seasonal index for decomposition, classical decomposition. We take average of D trend. Remember anyone? Section 2, how we calculate seasonal index or seasonal factor, index, or seasonal index using the classical decomposition. Recall that we take average of the different value for each of the particular month or particular quarter or particular season for each of the particular season. Okay, say for we have monthly data, then we take average of the different value for January, and then you get seasonal index for January. And then you take average of the trend value for February only, and then you get seasonal index for February. So basically using the trend value, that's why here we remove the LT. So LT is just like we are producing the trend. Okay, so I mentioned just before, LT is just equivalent to the time estimate. Okay, LT is equivalent to trend estimate in the classical decomposition. Okay, so we use the trend value to update seasonal index. Right. So this one, the new information y minus the yt minus lt to give us the trend value. Okay, and then we take into account the previous estimate of seasonal index, the previous estimate in time t minus s. Okay, because this is the previous estimate of the seasonal index for that particular month or quarter. Okay. Then after you update all component level, BT, growth for period, and then seasonal index, and then you can use this all these three after values to produce forecast. So FT plus M for one step hit in sample, T plus 1. Okay, so LT plus how many step hit M, how many step hit. If one step hit only one, we just want to produce forecast using information at a time at time T, and want to produce forecast for the next one, T plus 1, that one step hit. Okay, so if you just want to produce forecast for the next one using information at time T, LT, BP, ST. So I mean the seasonal index, we have to use the one for the same season. That's why we have T minus S. Okay. So let's say you want to produce forecast for January, and then you have to use seasonal index for January, the last updated one under January as well. So T minus S, T minus S means that using if you have monthly data, T minus 12, T minus 12. Okay, you have quarterly data, T minus 4, T minus 4 for the S season, number of season. So if for 2 step hit, you have to multiply by 2 or 3. Okay, 3 step hit, M equals 3. So S is the length of seasonality, the number of season. So example, S equal 4 for quarterly data, S equal 12 for monthly data, S equal to 2 for semi-annual data, S equal to 52 for weekly data. So weekly, weekly one year has 52 weeks. Okay, so S number of observation in a year per year. So monthly data 12 observation, quarterly 4, weekly 52. What is the minimum 2 lah. So there's another one we call as we have 6 observations per year also possible. 6 observations per year meaning that for every 2 months 1 observation. So LT represent the level of the series, BT denote the trend. So don't confuse, just now I mentioned that LT is quite equivalent to the value of trend for classical decomposition. So BT, we call that, it is called as trend. It is represent growth one period. In terms of the name, we also call it, or not called as trend, but just don't confuse. I should do level representing just like equivalent to value of level or the value of trend when we perform classical decomposition. But it is growth. How many, the amount of increment from one period to another period. So ST is the seasonal component, FT plus M is the forecast for M periods ahead. Alright, so to determine the initial estimate of the seasonal indices, just like the previous two methods, SES, single as corresponding as well as whole linear, before you update, you need to have the first value of LT, the first value of LT, the first value for BT, first value of ST. So they want to set initial value, to set the initial, to determine the initial estimate of the seasonal indices, we need to use at least one complete season data. That is S period. S period, it depends on whether you have 4 data, you have 4. Just now, you have monthly data and 12, as equal 12. So the level is initialized by taking the average of the first season. So to get the first value of level, we just take average. So this one, the one that I explained in lecture note, is for the purpose of manual implementation of this approach. So there are many ways to set initial value. Computer software use different way. Later on, you see that if you use other software, basically you can set, use different way to set, in a way that they set the initial value starting from the first one. So even if you use, it can set the value of L at the first value at L1. Okay, meaning that if you use R even calculate the initial value at time 0, one step before, one before that. Okay. So this one, the expression given here, if let's say we perform or implement that manually, okay, so we can use this approach to set the first value. So according to this one, we set the first value at time S, meaning that the value of the first value of level we calculate for the time at the end of the first year, so at S. Okay. Although it's also possible, there are other way lah. But computers use more complex approach to do calculation. But with this one, we just, because for this one for minimum calculation, so we use the simple way lah. Okay. To set the first value of L level, but we calculate for the last one. The last one in the first year, within the first year. So at S. If we have monthly data, then our first value of a level is L12. If we have quarterly data, L4. Okay. It is obtained by taking average of all observations in the first year, within the first year. So note that this is a moving average of order F, and so we'll eliminate the seasonality in the data. And then to initialize trend, the BT, it is convenient to use two complete seasons. So you need to have observation, you need to use observation for the first 2 years. Okay, so what you need to do, you calculate the difference between, because BT, it represents growth for 1 period. So we want to calculate, to estimate growth increment for 1 period, average increment for 1 period. So what we can do here, we take the difference between two values of the same season. Again, if you have monthly data, the same month lah. So in January second year minus January first year, divide by how many observation per year? 12. Okay, and then you do the same task. The difference between February of second year minus February the first year, divide by 12, and then do the same up to December. Okay, so each of these give us estimate of growth for 1 period, because this one, the difference between, if you consider monthly data, so the difference between January this year and January last year, so it provide growth for 12 period, right? For monthly data, 12 period. So that's why we need to divide by S, divide by 12 to get only one for 1 period. Okay, but this one for January, we have one estimate for 1 period, growth for 1 period, plus for February we have another estimate of growth for 1 period, March until December. So in total we have 12. So we need to divide by 12 again. Okay, so this one for 1 period, growth for another period based on February, growth estimate of growth for 1 period for March until December. So in total we have estimate of growth for 1 period 12, huh? So 12 times. So we need to divide again by 12 in order to get growth for 1 period. Okay. So each of these terms is an estimate of the trend over one complete season, and the initial estimate of BS is taken as the average of S such adjusted. Okay. So this again, so the first our estimate start from the last one in the first year. And then the seasonal indices are initialized by taking, for the seasonal index, initialized by taking the difference between the first few data values to the mean of the first year. So just like I mentioned before, so we take the difference between each of the observation the first year minus the level. So it just like the trend. So just like the trend, remember decomposition, how we calculate the trend, how we calculate seasonal index by taking average of the trend values. So basically where we are. So this one seasonal index for the first month for January, it is the difference between observed value of Y at time for January minus the first estimate of level. So we just give us again just like the trend value based on January value. Do the same for February and so on. So the smoothing parameter value are chosen to minimize SSE or MSE. Although you can assign any value, there is no what we call, it's not compulsory to do the optimization. Okay, but the easy way, because how to decide? Okay, how to decide the suitable value? So one of the suitable way is by finding value of smoothing constant alpha, beta, and gamma that give us smallest value of SSE. That's what we call true optimization. And then several other methods for optimization are also available. Later we will see what we call a heuristic scheme. The one also explained in the additional note. The method used in R by R. I mean the code available in R for us to implement this exponential smoothing method. So if you get to the Excel file, I think it's one. So we have, this is housing start data. So if you inspect the reproduced graph, so you can see this one. So in terms of, in terms of the trend, it doesn't seem to have trend lah, but it's horizontal. In general lah, although there's no deterministic lah, because there's no deterministic trend. Deterministic is continuously increase or continuously decrease. So we have later we discuss there are two types of trend, deterministic and stochastic. The one we discuss in the future lecture or topics. So in terms of the seasonal variation, it doesn't seem to have based on graph inspection, it doesn't seem to have what we call that increasing or decreasing magnitude. Okay, so we can try to use additive. First one additive, what we call it Howitter's additive. Okay. So you have data, what you need to do, you need to set the initial value first for LS. LS meaning that we have monthly data, so L12 lah. Okay, L12. Set the first initial value. I mentioned again, if different software, if you use computer software, it's possible that you provide value from the first one. Okay, but if you use manual calculation, then we start from the L and S, because the equation later on it requires us to, when we update the level, we requires ST minus S, ST minus S, so ST minus 12 for monthly data. So that's why we have to start from here, initial value, if we do it manually. Okay, so set the value of the initial value of the level by taking average of all observation in the first year. So take average, so you get this one, 2. And then we also calculate the first value for growth for one period TT, or trend is what we call as trend. Growth for one period, because it provides the amount of increment. So that's why it is called trend. Okay, but again it is give us estimate of growth for one period. So to get this, so we do just like what I explained just now. So we take difference between. So it just to what we call it, to let you understand. But later on, basically, we are going to use use and R. Okay, to just for you to understand how it's obtained, for example. So this one way to set initial value of the probability is by taking the difference between each of the same month, second year minus the first year, divided by 12, we got monthly data, and then do the same for February, March until December, and then in total we have 12, and then divided by 12 again. Yeah, so we have them. And then set initial value for seasonal index by taking the trend, just like calculating the trend value. Okay, the trend is just like the classical distribution, okay, average of the trend values. So this one, the trend value based on February of January minus this one. Observed value minus the LT gives us seasonal index for the first one, and then we do again for the February and so on. So we have initial value for the first 12. So seasonal index for January, February, March, April until December. Okay. Seasonal index is a different season. So that's why we have 12 season, 12 month, 12 season. So seasonal index for each of the season. Season 1, January, season 2, February, season 3, March, and so on. Yeah. And then after that, you can, whenever we have new information, so we update lah. So we added using the first equation. So let's say, okay, let's say that this one, you initially put 0.1 for example. Everything you put 0.1, this one 0.1. And then later, we through optimization, we find the optimal value. So let's say here, you can just, again, alpha, beta, and gamma, you can put any value. Alpha, beta, and gamma, although you can sign normally, it must be between 0 and 1. Okay, alpha, beta, and gamma must be between 0 and 1. So that it is, the calculation is done based on weighted average. Okay. Any value is acceptable, but what is the suitable value? That is suitable. You need to use a suitable value. Some says that just use small value of alpha, beta, gamma, so that the assumed value will not affect too much of this update, the revise or update when we update the value. But some suggest select or identify value through optimization that give a smallest error, the size of error as SSD. Let's check it out. So let's say we initially put 0.1 first, 0.1 between 0 and 1 and 0.1. Let's put 0.1, alpha, beta, and gamma, and then we update. When we have new information, so we update level based on the first equation, is 1. So 0.1 of the adjusted value, okay, and then we take 0.9 of the pre-estimate, okay. Formula, so we get this, and then after you update level, we update the growth of BT or update trend by taking the difference between two levels. Okay, the last two levels is one, and then also take into account the previous estimate of trend. And then we do the same whenever we have after we update both. And then we can, to update seasonal, we just need this one, the updated level. So basically using the last equation, using this one, the third equation. So we update seasonal index by using the trend, just like the trend value, the last or the recent value of the trend value, and previous estimate of seasonal index. So notice that this one, we take a portion of the difference between the last two, the different, just like this value, so y minus l, yt minus lt, and plus a portion of the seasonal index for the same month, the same season, the previous one, same season. Because this one for January, you have to take January. Do not take the December, because this one season. So ST minus S, ST minus S. Okay, so T minus 1, 2, 3 up to the last one, T minus 12. Okay, so you have to use the index of the same season. You want to use forecast, you want to update seasonal index for January, and then you update using the last updated value of seasonal index for the same season, January as well. Okay, later when you do for February, you use the for the previous one, the previous February. Okay, so this one you need to be careful. So do not, when you update seasonal index, do not use the previous one, but use the last, the previous, previous value for the same season. Okay, T minus S for quadrieta, T minus 4. So that's why we have this, for manual way of calculation, we start from LS because this one we have to use the last 12. So once you update everything, then you can use that to be forecast. So LT plus BT plus ST. Okay, so to produce forecast, L the last updated level plus last updated growth or trend for a period. A group of period or trend, and plus mean that for that corresponding or for that particular season. So you want to use forecast, this one, forecast. You want to use forecast for January, this one, forecast for January. So we take L, the previous estimate of level, plus previous estimate of growth or trend for one period, a group of period or trend, and then plus seasonal index of the same season. Same season, not the previous one, but same season. Okay. So January, because this is the forecast for January, so you take that for January. Yeah. And then when we have after that we have a new observation, or we do the same update level using the same formula, update trend, same formula, update seasonal index, same formula, and include forecast. Okay, for example. Okay, so now what is the value of optimal value of alpha, beta, and gamma? So you can find optimal value through optimization, just like how we did last week using Elsa solver. So you go, you select data. So this one, so we take the difference after you calculate forecast. the difference between actual minus forecast equals error. Okay, error. So we want to minimize this error, sum square of error, SSE, sum square of error. So we form optimization by we go to data, select solver, Excel solver. Okay, so we do it again. So we do it. We reset all. Reset. So how to perform optimization? We want to find the value of SSE. So our objective is to minimize SSE. So this one, choose SSE. This one, choose SSE because we want to minimize this SSE. The sum square of error. And then minimize, not maximize. If you select maximize, you find the maximum value of SSE. Okay, you select, you just use one, maximize. You find value of alpha, beta, and gamma that give maximum value of SSE. So select minimize. By changing discrete alpha, beta, and gamma. So by changing, you select this one, changing alpha. Do not select this. Do not select the name. Select this number value. Okay, highlight the value. Cell for the value. And then recall that if the alpha, beta, gamma must be within 0 and 1. So we need to put or impose restriction or constraint that all the three alpha, beta, gamma must be between 0 and 1. So this one, you subject to constraint, you add constraint. Add constraint that these three alpha, beta, gamma, you can do one by one also can. Okay, but you also can just select all three together. Alpha, beta, gamma less and equal 1. Add. And then you do another one, repeat, select this one again, and then this one greater equal 0. Okay, add, and then click cancel. You click cancel and check everything correct. So you want to minimize SSE, minimize by changing this one is 3 alpha, beta, gamma. By imposing constraint that this 3 alpha, beta, gamma must be between 0 and 1, less than 1, greater 0. Then you press solve. Press solve button. Then just okay lah. So it gives us the optimal value. Alpha, beta, gamma that give us smaller value of SSE. That is alpha 0.8423, beta 0.0042, gamma 1. Okay. And then for our sample forecast is one. We no longer have new information, new observation. So how to produce forecast using the last equation is one. So LT plus M times PT plus the corresponding sine index. For one step ahead, for our sample, just the same. So the last updated level plus updated trend plus sine index for the same month. The last one, the last updated sine index for the same month for the original. And then for two step ahead, the last updated level plus 2 times this one, 2 times PT, because 2 step ahead we produce forecast for the next 2. Remember, BT is a growth estimate for one period, estimate of growth for one period. So if you want to do forecast from the last value to the next point, the 2 points, so must multiply by 2 lah. Okay, this BT plus 2 and then plus the index for February. And then do the same for the next one, 3 times growth. The last of the level, at time T, LT, so LT plus 3, LT plus 3 equal to LT plus 3 times BT plus seasonal index at time ST plus 3 ST plus 3 minus 12 plus ST plus T plus 3 step 8 minus 12. Mana? Yeah, itu the same. So you notice that for the first year, for second year, this one, second year, you want to do forecast for the following year, January of the following year. So again, the last of the level plus the last available BT times how many times? It is January next year. So one step here, two step here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, this one, okay. So this one, the last one, November, okay. That's why 14. So you notice this one. For December, we use the last method. For this one, November, because November we use the last one. But after that, for the next one, we don't take seasonal index. You notice that for November, because we have data until the last one, November, the last one is for November. So you take this one for this one, but for the next one, you have to do for this one. For the next one is December, so you have to take the last one, the latter one, for December. Yeah. So that using additive, Cointer's additive. Now, manipulative, we have the same number of equations, 4 equations, but for the first and except for the second one, so the other equation has slightly different. Okay, for example, the first one, to calculate, I mentioned before, to calculate the state adjusted value instead of minus, you take a ratio. Remember, classical decomposition, for the case of multiplicative decomposition, to calculate sin adjusted, you take ratio divide YT divided by S to remove the seasonal component or to calculate to get sin adjusted. So we take ratio instead of minus, we divide. Instead of minus ST for multiplicative, we divide sin index for that particular season. And then this one is exactly the same. For sin index, we take ratio as well instead of minus. Instead of subtract LT, we divide YT divided by LT to get the trend value. And then for forecast, LT plus M times BT, everything, the whole thing multiplies in index. Okay, it's not plus, but it's not multiply. So equation 2 is identical to equation 2 of the additive model. The only differences in the other equation are that the seasonal indices are now multiplied, divided instead of added or subtracted. The initial value of LS and S are identical for the additive model, still the same. Okay, but for the seasonal index is slightly different. Now minus by we divide. To initialize the indices, we use ratio between Y and each of Y, the first observation, first year divided by the the initial value of the level S. So data given here. So the second same Excel file, the second data set. So this one you inspect data, you insert produce graph. You see it. So this one is it has trend, it has multiplicative, seasonal variation. Okay, as the value increase, the size and magnitude of the seasonal variation increase in the size. So we use added multiplicative, Hovitas multiplicative. So the steps are quite similar. To set initial values as the same, to set the initial value for LT and BT as the same. Initial value for ST just slightly different, instead of minus, just divide, take ratio. And then after that you can update. So update equation, okay, using the first equation, the first update equation. This one second equation, update seasonal using the third equation. And then you can produce forecast. Okay. Forecast that is given by the last update level plus the last update growth. Everything in bracket in plus this one first and then multiply the index. Multiply, not plus. Multiply. And then you can take difference between actual minus forecast gives us error. And then you take the sum square of all error, you get SSE. Sum square of all error, you get SSE. Okay. Now let's say we do the same here, optimization. Initially we put 0.1 averaging. If you impose the constraint between 0 and 1, this one, the starting point for optimization, you should not put value outside the what we call the range now. Do not put 1.5. It cannot. When you run, it cannot run. It will not perform optimization because starting point already outside. Okay, outside 0 and 1. So this one, let's say 0.1, you just put initial value, starting point, and then you do the optimization, data, server. You just select for other step, you select this one, this already have here. This one, SSE, minimize, by changing alpha, beta, gamma, constraint, and then you just run click solve. So you provide the optimal value, alpha 0.8323, beta 0.0107, gamma 1. So meaning that gamma the maximum value. So for the additive just now, also the same. So it suggests the maximum value allowed between 0 and 1, so maximum 1. And then after that you can produce forecast for our sample, also the same. So one step ahead. The only difference between the sample and our sample, for 2 step ahead, you have to start multiplying by 2 the level, BT. 3 step ahead, BT times 3, and so on. Okay. And then you also need to be careful for manual calculation for signal components and index. After the first year, second year, you have to rotate. The last updated one, the last updated signal index. Okay, now the same data in if-use, we also can do if-use, but I mentioned before, if-use, the different software use different way to set initial values, and also different way to implement optimization. So the outcomes of the estimate won't be the same, just like how we produce using Excel just now. So we have data for audience sales one, if-use, audience sales data. For the Hovitas additive, this one. So we have the data just now, graph. You produce graph, you get this one. So it doesn't seem to have what we call consistent increment in the magnitude of seasonal variation. So maybe we can use what we call additive. So we use additive. You go to prop, Select exponent smoothing, simple exponent. So simple exponent smoothing refers to the classical version of the exponent smoothing method. So we have a single exponent smoothing, or vectors, whole linear, or vectors additive, or vectors multiplicative. So we choose one, simple exponent smoothing, select whole vectors additive. Okay, so this one, alpha, beta, gamma. Again, if you want to assign any value that you prefer, different value, I mean any what we call the value that you want to use. For example, 0.5, then you put 0.5, 0.5, and so on. But this one, you put E if you want to estimate the optimal value. You just put E for estimate. YSN, our forecast value lah. We just like in Excel just now with this one, the forecast FT the forecast. So in sample, one step 8 for our sample, multi-step 8 YSN. For our sample, whenever we no longer have new observation, then it start to calculate forecast for multi-step 8 1 step 8, 2 step 8, 3 step 8 from the last one, the last observation we have. In sample or the duration of the sample. So YSM based on this equation, YSM based on this one. Additive just now, additive model this one. Okay, there's more YSM. Okay, so you get alpha 0.9, beta 0, gamma 0. So unlike just now, we use Excel, we get 0.84, beta 0.0042, gamma 1. Means alpha almost quite not that much different, but beta and gamma, you just choose 0. Okay, 0. So this one mean trend, the end of period. It's just like the last updated value of LT, the last updated value of DT, the last updated value of ST for each of month. This one for December, January, and so on. This one the last updated value of LT, DT, and then the last updated value of ST for the 12 months starting from December. This one the last updated level, the last updated BT, growth or trend, the last updated ST. This one so if you give us the last one. Okay, the last value of the updated mean LT, trend BT, seasonal ST for each of season. So we have for the 12 last seasons. So you can use this to calculate forecast. Let's say you want to use forecast. If you have this value, then you want to calculate forecast for the next one step in forecast or 2 step in forecast. Then you can use this one. So if let's say 3 step in forecast, how to calculate? This one, the last updated value of LT plus 3 times of BT, 3 step here, plus 3 times of this, and then you plus that particular season. Let's say for this one, because the last one November, so the next 3 step is supposed to be February. So you take as the last updated season date for February for 3 step here. Okay. Okay, another one for multiplicative align data. So you can inspect produce graph just to get idea which model is the best or most suitable. So look at the graph, it has trend, it has seasonal variation, which is multiplicative seasonal variation or multiplicative seasonality. So we use Howitter's multiplicative lah. Okay, Howitter's multiplicative. So again, you go to prop, select exponential smoothing, simple exponential smoothing, select Howitter's multiplicative. Howitter's multiplicative, the last one. So again, alpha, beta, gamma, whether you want to put any value between 0 and 1, or you just ask if you use to estimate. So put E, and then YSM for the forecast value, FT. Okay, just okay. So you get estimated value of alpha 0.1, quite similar like before. Just quite similar to the additive one beta 0 as well, gamma 0. So the last updated level 3, 4, 3, 4, 2, and then trend. So if you click YSM, you give you forecast. So this one for one step ahead. Forecast, and then starting from our sample, the last in sample data is December 1956. 56. December, that's one. So this one step ahead, one step ahead, two step ahead, three step ahead, and so on. Okay, so now we go to lecture 5. So this one first. Okay. What is one? Lecture 5, classification of exponential smoothing method. Okay, so previously I explained to you we have two types of seasonal variation, additive and multiplicative. So far you understand the difference between additive seasonal variation as well as multiplicative. Okay, additive when the seasonal variation and magnitude seasonal variation is constant or similar for the entire data set. Multiplicative seasonal variation when if the level increase, the magnitude of seasonal variation increase. They want multiplicative. Now for the trend also can appears or can be the same. It can be either no trend, just like just now. For the case of additive, for the case of this data, when we produce graph of the series just now, it doesn't seem to have trend. A trend, there is no upward or downward trend. So meaning none. Okay. So the trend, if the horizontal, there's no trend. Okay, horizontal none. Or there is also possible to have additive trend or multiplicative trend or additive dampened as well as multiplicative dampened. So if you open another, the example given another file, this one. This is an example of no trend, no seasonal. So this one is what we call base of pages classification. So no trend, no seasonal. And then if there is no seasonal variation, but there's an additive trend. Additive means that the increment mean the amount of increment to be constant. Okay, for every one period increase, the amount of increase in the speed also the same. So this one we call it additive, or just like linear trend, linear or additive trend. Okay, additive, and then we also can have multiplicative trend. This one, multiplicative trend. So in terms of equation, it is something like this now. So additive just now is the level plus this one level plus B is BT growth and then H how many times hit. So we see L and the LT plus BT is like additive. So manipulative in terms of the graphical representation. It is it behave like this now. If the series, the trend is non-linear, something like this. So this is what we call as multiplicative trend. Okay, multiplicative trend. And then we have the other two types. We have just now. So we also can have what we call the additive dampened or additive dampened or dampened. Okay, so this one, if additive based on this one, if additive this but dampened trend, meaning that over the time the amount of increment getting smaller. Okay, you look at to the second graph. This one dampened trend. So this is a linear or the additive trend. This one additive dampened. Okay, so it's not. I mean, FT increase 1 unit. The value of series increase, but smaller, which means smaller amount of increment. Okay, this one dampened trend. So you get to the other, and then we also can have multiplicative. So multiplicative dampen as well, something that multiplicative like this, multiplicative, but you also can apply reducing rate of increment. So that one we call dampen, multiplicative dampen. Okay, which is based on this. The trend is based on the equation. Okay. So in total we can have 15. So this one based on the first classification. The first classification in 1969 only suggests, I mean there are only 9. Okay, 9 categories. Okay, 9 types of combinations between trend and seasonal. So this is trend, this is seasonal. So this one no trend, no seasonal, no trend but additive seasonal. No trend, multiplicative, seasonal. So this one additive trend, no seasonal, additive trend, additive seasonal, additive trend, multiplicative seasonal. So this one correct multiplicative trend, no seasonal, multiplicative trend, additive seasonal, multiplicative trend, multiplicative seasonal. So now for both trend and seasonal we can have both additive and multiplicative. But for trend we also can have, we can further divide the additive and multiplicative into two, the dampened and not dampened, dampened and not dampened. So in total we have 15. If you refer to this one, in total we have 15 classification of the exponential smoothing. Or I mean this is a classification of the times data in terms of the patterns of trend, the pattern of seasonal. Okay, you can have 15. So if NN, no trend, no seasonal. NA, no trend, additive, seasonal, and so on. So M for manipulative. So this small d for tempered trend. That's one as well. Okay. So just now, I mean previously, last week and just now, we discussed about the four models. So we have single exponent smoothing, which is this one, which is suitable for the series that categorized under this category. And there is no trend, there is no seasonal. Okay. Collinear, which one? Collinear, we have trend, we have no seasonal. Okay, so we have trend, no seasonal. So I did this one, I did this two. And whole linear, this one, I mean no seasonal. This four, so either this, AN, ADN, MN, and DN. Okay, whole linear. It depends on, I mean, whether it's as multiplicative or additive. Okay, but if the trend is linear, then you just do this one, EN, additive trend, and no, what we call that, seasonal. And then Howinters which one? Howinters additive. Additive seasonal. This one, this column. So in terms of the trend, it depends whether it has trend or not. If it has trend, it depends on the type of trend. So if you get to the example that we have right now, this one no trend, no trend, but it has I mean, if you consider it to have additive seasonal, but later if you suggest multiplicative, okay, because it's select based on the value of or through optimization value of SSC. So basically, Howinters additive must be under this column. Okay, this column depends on whether it has trend or not. Howinters multiplicative is one, the last column. Howinters multiplicative, the last column. Okay, but using the classical exponent smoothing, we only have four models. We only discuss four different equations or different model. But I mean, it is. I mean, when we use that one, I think the equation is actually quite additive. It's like an additive trend. So additive. So meaning that it's not really whenever we use whole linear, for example, it's not really the best one. I mean, to represent the correct pattern of the trend. Yeah. Okay, so now these 15, some of them are the one that we discussed before. Whole single, exponent smoothing, SES, whole linear, Howinters, additive, Howinters, multiplicative. But we also can expand that to cover 15 types of different classification depending on the type of trend as well as seasonal variation. So this one we have NN, simple smoothing, and N, the one that we discussed earlier. No seasonal, no trend, no seasonal method, and then we have whole linear. Or basically, it is quite the best. It is equivalent to the EN category. So additive trend, no seasonal. And then we have tempered trend model, so A. So additive trend with damping coefficient, so dampened, and then seasonal additive. Howinters trend and seasonal method, which is given by this one. So we have EM, additive trend, multiplicative seasonal, and then additive, both in additive trend, additive seasonal. That's the four model we discussed before. The four model. So meaning that the four model we discussed before only provide model for 4 out of these 15. Okay. And then now we only have different pattern for seasonal and trend, so whether it's additive or multiplicative. And in addition to that, we also can have additive and multiplicative for error term. Error term is the difference between actual minus forecast. Okay, so actual minus forecast give us can also be in the form of additive and multiplicative. So so basically the 15 different classification is one we can convert and express in alternative form, which is the one that we call as stick space model. Stick space model, which is explained here. Stick space model, which is we use this one, the triplet ETS, because just now we discussed about trend. Trend can be additive, can be additive, multiplicative, as well as additive, dampened, multiplicative, dampened. Seasonal S can be additive, can be multiplicative. We also can have the error E. Error can be additive and multiplicative as well. Okay, the error is between observed YT actual value minus the forecast. Okay. So you refer to this one. So this one actually additive. If additive, it means that additive error. So the error is just the what we call the difference between observed and forecast value, or forecast value or the mean value is just the error. So and then for the case of multiplicative, the difference between YT minus UT minus the forecast, the actual minus forecast, it is the multiplicative form. So meaning that the ET times UT. So later you can have this one. Okay, so it takes time for you to understand. Please go through this one. So basically we have two types: additive error and multiplicative error. So we can expand now. We can expand the 15 classification into 30 models. Okay. So just now we discussed this one. So we have 15 classification for trend and seasonal, and then each of these can be categorized into another two model that has either additive error as well as multiplicative error. Okay. Now each of these we can convert to the equivalent stick space version. So if you look at to this one, so what is the stick space version of exponential smoothing? You look at to this one, stick space model. Okay, this one. So this is an equivalent model for whole linear. Maybe just now we have TS, trend additive as none. It is equivalent to whole linear, right? Whole linear, but whole linear with additive error. Okay, whole linear with additive error. So ETS, EEN. Okay, how we can convert from whole linear to the ETS, EEN? If you refer to the notes I provide here, just this one, just an example how we convert. This one. Whole linear to ETS. This one is just to give you an idea how we can convert the classical version of exponential smoothing to the model version. We call it as the stick space version, stick space model. But don't worry much on this one. I will not ask you to prove in exam. It's just example, how we convert whole linear additive whole linear model to the ETS AAN. So meaning that just now we know that whole linear is equivalent of EN, ada calculation for EN. There is additive trend, no seasonal. Additive trend, no seasonal, EN. But then we also can have additive error. So for the case of additive error, this one additive error, we can convert the equation, and then we get instead of the forecast value, the last equation, so the forecast value. So for linear, this one for linear, this one. Okay. So we can convert instead of in the original equation, we can convert and then we get a new equation. For example, this one for whole linears to the ETS AAN, we get this, and then so later I will not explain detail this one. I will not discuss it because this one again I will not ask you to prove. It's very tedious to do. Again, this one is just to help you to get idea how we can convert the classical version of exponential smoothing to the state space version of the exponential smoothing. Okay, using what we call as ETS model. So if you use this, later you can have a look at this one. So we can convert and we get this. So eventually we have this one, this model. This is ETS model that is equivalent to the whole linear model. So this one we use to update. Instead of we update level using the original equation, we update this one we update level. Okay. Alternative equation for this one to update level is given by the equation. Okay, which is the previous level plus the previous growth for one period and plus the smoothing constant alpha times the error term. So in the original version we don't have error. Okay, but we can convert and we have alternative equation that is equivalent for the whole linear model, which is given by this. To update level, we use this one equation, and then to update growth, we have this. How we obtain this one is given here. Actually, this is just this one. Okay, how we convert. Okay. So this is the ETS. Okay, ETS AAN. This one is the recent version of the exponential smoothing model. The classical version is already introduced many years ago, maybe 20, 50 years, 60 years ago. But this one, I think around 2000 something, 2008, around that, they produced the book. So for the new version of the exponential smoothing model. So this one, ETS AAN, is equivalent to whole linear in the classical version. And then also can have this one for the whole linear but multiplicative error, so which is given by this. Okay. So we have in total, I mean we can do the same for other models as well. We can convert from the 15 classification. This one, the 15 classification we have here. Okay, this one, this is single exponential smoothing. This one whole linear. Alright. This one single exponential, this one whole linear. So we have hot Winters additive. This one hot Winters additive. Okay. So we have 15. The 15 classification just now, all given here in terms of equation. So each of these model can be transformed to the equivalent state space version using this one. For example, using this approach, for example, to convert, then we can eventually we have 30 different models. So we have this for additive error, the 15 different model for additive error, and then 15 different model for multiplicative error. Okay, so we have in total 30 different ETS model. Okay. Okay, in terms of to set initial value, if you use R, for example, function in R, you use this approach to set initial value, so L1, B1, S basically R it calculate for time 0, L0, B0, S0, not even A1, S0 as well. Okay, so later you can run again. I will not ask in detail how it is calculated, but I mentioned just now. The method that we use, just a simple way. I mean, just now when we do the manual calculation, just a simple way. So basically, software use more advanced or more complex way to calculate initial values. Okay, and well, we also can perform optimization by estimating initial value as well. Okay, so R also can basically, if we do not specify, R will perform optimization by estimating the initial value as well. Okay, it calculate using this approach, and then after calculate the starting point, and then it when through optimization it find the value of initial value that gives smallest SSE as well. Okay. So this one you can read later. This one just give you an idea how it set the initial value L0. Not even L1, it says. If user not sure, but I want to calculate for L0, B0, and S0. This is the index for the at time t equals 0, not 1 before that. 0. And then estimation, you use the maximum likelihood, okay, to perform estimation to estimate the parameters, the initial value as well as the parameters. Okay, and then by imposing restriction for the value of alpha, beta, and gamma according to this one. Okay, so basically if you refer to I mean later you can read this one, you go through. So basically the alpha, beta, and gamma is not exactly the same in the classical version and the new version ETS. Okay, because ETS, if you read this okay, this one, so basically the beta in the ETS equivalent to alpha times beta in the classical version, and then gamma equal to this in the classical version, and then so on. Okay. So in total we have 15. We have 30 different models. The 15 classification for additive error, 15 classification of trend and seasonal for multiplicative error. So we have 30 different models. So if you go to the EViews, so for the ETS, we are not going to calculate manually. So we start discussion by using manual calculation for classical version, just to get you an idea, to help you to understand about the concept of exponential smoothing method. But we are not going to do what we call the same calculation for the ETS. We just use software. So you go to the lecture 4, back to lecture 4 folder. The data that we used before for single exponential smoothing, it is this one, opponent run or inventory, opponent inventory. Opponent. Can opponent this one? Okay, so this one. So if you check the previous graph, so there is no trend, right? There is no trend. So because this is annual data, so there is no signal. It's annual data, right? You know. So there is no trend, there is no seasonal. So previously we used single exponential moving. Okay, single exponential moving. Now we want to use ETS. Which model is equivalent to a single exponential moving? SES. It is ETS what? ENN. No trend, no seasonal. Right. So you go to prop exponential moving ETS. Alright, ETS exponential moving. So if you want to estimate a model that is equivalent to single or simple exponential moving, so which is ETS, it's supposed to be ETS A additive, none for trend, none for season. Okay, so ANN. So similarly, if you want to set any value of alpha, you can put here. Otherwise, it will estimate for you. If you leave it blank, then it will estimate the value of alpha. So this is a estimation sample forecast from this point. So we have data until November. So this one until the last forecast we use. Then okay lah. So this one model selection. This one left. Output forecast YSM as well. Okay lah. Let's click okay. So the chosen alpha 0. Okay, chosen alpha 0. Then initial. Here it only provide initial value of the LT, initial value of level LT. It does not provide the last. Unlike the classical version just now, it provide the last updated value, but this one it provide the initial, the first one. Okay, initial value at time 0. I'm not sure if used, but R is at time 0 lah. I haven't investigated. So initial value, so of level. Forecast juga given here. Okay, so one step ahead. So basically the same lah, because we just flat forecast just like how we did before. For the case of SES. Okay, another example, hot linear inventory. This one hot linear. Okay, this one, if you just now, if you choose model, then you can just let auto. You put auto, everything auto. But this is not for this monthly data. This is for open. Because we put this monthly data. Okay, I mean if you put auto you will select for you. It's submission or measure because for auto signal cannot, because we have small sample size. So basically you can, okay, we do for another example, so we do for the case of inventory data. Inventory data, you do the same, you open, you go to prop, select ETS. So hot linear is equivalent to ETS what? If additive error, additive, and then we have additive, trend, no, seasonal. Okay, so we provide all 0. So that's why we have different software. I mean, you have to compare. So sometimes I think for ETS, I think maybe R is better than EBUS. In providing more makes sense estimate lah. Okay, this one can, but when alpha beta 0 means that we not update lah. It means that we not update, it's just the same estimate of level, estimate the same estimate of growth. Okay, then initial value of LT, BT, and now forecast YSM. So if you want to ask, or we want to, if you to select model for us, then just put auto lah, auto. Okay, and choose. So you choose what model? EMM. Additive error, additive trend, additive seasonal. Okay. So you put auto, then it will select model for you based on the smallest. You find model that gives the smallest. I think like you take it. Okay. So maybe this one unable to. It's not the best model lah, because it has some problem with everything. We go back to the for the seasonal one. So this one housing sales data. You go to prop, exponential, smoothing, ETS, additive, trend must be. It depends on this one. There's no trend, right? You expect the graph just now. Housing sales data, there's no trend, right? So if based on graph, then you can select none. But again, the season must be additive, right? Season must be additive. Okay. Okay, let's say based on graph we see that it is horizontal trend, then it's like none. And then based on your own judgment, and then seasonal, it's additive. If you think it is additive, okay. But again, I mentioned before, sometimes I mean, for example, because there's not exactly constant magnitude of seasonal variation. So you click OK, so you get this estimate E and A. So you get alpha 0.9, gamma 0, and then your forecast. If you use to choose model for you, auto. So this one, either you decide by inspecting graph whether it has additive or multiplicative or additive dampened. You can decide based on that, or you just ask if you to choose for you. Okay, by choosing auto. Okay, auto. So it suggests E and M. Additive error, no trend. Multiplicative. For even this one is a multiplicative for housing data. The last one we have the A9 data. A9 data, you go to export smoothing, ETS. So based on graph just now, it has either this one we're not that sure, but it has trend. Whether it's additive or additive dampened or multiplicative, not that clear enough for us. So let's say additive. Okay, but it has multiplicative, right? Multiplicative seasonal. Okay, so it's just the value also 0.9, and then if they say we ask if you to choose model for us, auto, and then all auto. So it's just MEN, multiplicative error, additive trend, multiplicative seasonal variation. Okay. our break. So after break, I will show you how to use R. How to use R to estimate both with the classical exponent model as well as ETS model as well. Okay, so we resume in 15 minutes. Have an hour break.
宝贝，坐到这里。